we're going to start by solving this Newton's law of heating problem. And we've solved these kinds of things by hand last week using separation of variables. This time, let's use Mathematica. Let's start to get some practice using Mathematica. The problem says cold water at 5 degrees Celsius is in a room. I didn't need the extra word degrees there. Is in a room with ambient temperature 22 degrees Celsius. After 1 minute, the water is up to 7 degrees Celsius. And again, we're assuming that we're mixing the water well, so you don't have to worry about spatial effects and you don't need partial differential equations. How long will it take for the water to get to 20 degrees Celsius? It went up by 2 degrees in 1 minute. If you assumed a linear model worked well, you would assume it goes up by 2 degrees every minute. It has to go up by 15 degrees. You might guess the answer is 7.5 minutes. But that shouldn't make sense because then it would overshoot the 22 degrees. It would get warmer than 22, and that doesn't make sense. You can actually think about these without differential equations. You can imagine an exponential model whose graph looks like this and just try to fit the data right away. But it's good to think about it with differential equations because what differential equations does is it gives you the flexibility to tweak the model to maybe account for, I don't know, a heater or a fan blowing periodically, and that affecting the ambient temperature, the local ambient temperature near the water. That's what differential equations gives you the power to do. And if you're trying to model without differential equations, you wouldn't be able to deal with complexities like that. Anyway, Newton's law of cooling is a fairly simple model. If I let Y be the temperature of the water, and you should say what the units say in degrees Celsius, T be the time in minutes, the model takes the form that the rate of change of the temperature with respect to time, dy dt, is proportional to the difference between the temperature of the water in this case and the ambient temperature. It's somewhat traditional to do that difference as the ambient temperature minus the temperature of the water in this case, and have a negative constant of proportionality, or actually, that would be a positive constant of proportionality. You can do it either way. This quantity, this difference, gets multiplied by some constant of proportionality, which you can call K if you like. If it is Newton's law of heating, and if Y is less than 22, that's going to mean 22 minus Y is a positive quantity. The water's obviously warming up, so you'd want your constant K to be positive here. You could do it the other way. You could do the difference as Y minus 22, but if you did, you'd want the constant of proportionality to be negative, and you'd maybe want to write it as negative K to emphasize that. Either way you do it is okay. If you do it this way, K is positive, but negative K is negative. If you do it the other way, with a 22 minus Y in there, then K itself would be positive, and it would be the constant of proportionality. The key thing is you need dy dt to have the right sign. It's warming up, so dy dt is positive. So you need, on the right-hand side, a quantity that is positive when Y is less than 22. Actually, I'll do it more this way. This is the more traditional way to do it. Y minus 22 would be negative for warming cold water. So I need to multiply by a negative constant to get a positive quantity in the end. But I might want to emphasize K itself is positive here. All right. How do you solve this with Mathematica? There's a couple commands that can be used. One is dsolve with a capital D and a capital S. I like using a little bit more specialized version called dsolve value, but either one is okay. Dsolve value, capital D, capital S, capital V, capitalization in the right spots is essential in Mathematica. Then you put square brackets, and this version of Mathematica automatically puts the n square brackets in for you. I just typed one of those, and the other one showed up automatically. That's a good thing in general, that it does that for you in this version of Mathematica. You want to put the differential equation into the input of this d-solve value Mathematica function. You also want to put the initial condition, which is 5. Y of 0 is 5 here. And you want to put those two things, that differential equation and that initial condition, into the d-solve value in what's called a list with curly braces, which I can type one of them and Mathematica will end it and type a second, end curly brace. Earlier versions of Mathematica, you got to type both of them. How do you type the differential equation into Mathematica? Do you type dy dt? No, don't do that. Type y prime of t with square brackets. Mathematica functions, whether they are things like d-solve value or a y of t, have square brackets for their inputs, not parentheses. Very, very important. It's also very, very important, this is the most common place people make a mistake here, to put double equal signs. When you are having Mathematica solve equations, double equal signs is essential because single equal signs will assign values rather than solve equations, and that there is a distinction there. We're not trying to do like you do in computer science where we're trying to set something equal to something else. We're not assigning a value here. We are trying to solve an equation, and Mathematica distinguishes between those. Single equal sign in the first case and double equal sign in the second case. This is the most common mistake. People will often do just a single equal sign and it causes trouble. Okay. Double equal sign. How do I do the right-hand side? Do it like this? This is the first thing people would guess, but it's not going to be quite right. You need to emphasize to Mathematica once more on the right side that y is a function of t. So next to this y, I need to put a square bracket t. The parentheses are used here and here. That's for multiplication. Negative k is getting multiplied by that entire expression, y of t minus 22. So parentheses are more for multiplication in Mathematica. Square brackets are for function inputs. These are essential things to know. Then you put a comma. We're still within the curly braces here, this list. The first thing before the comma is the differential equation. After the comma is going to be the initial condition. Y of 0 equals, doubles equal signs again. 5, right? The water is 5 degrees Celsius at time 0. Double equal signs are necessary here too. We're ultimately trying to solve for an unknown function. We're not trying to set things equal to something else. We're trying to solve. Tab over to outside the curly braces and put another comma. So these things are that go into the d-solve value are separated by commas. The first thing is a list with two things in it, the differential equation and the initial condition. Then you put a comma after that. Then you emphasize what is the function you're trying to solve for, y of t, put another comma, and then you type a t. Why do I need to emphasize y of t is what we're solving for, and then the t is the independent variable? It's because you could have other letters in here, like the k, for example. And I'm not saying what the k is in Mathematica. I'm not saying Mathematica k is 4 or 0.2 because I don't know what k is yet. I want it to be able to solve it, not yet knowing what k is, and it can do it. This is syntax that will give us an answer when I enter it. On a small keyboard, you enter this by making sure your cursor is somewhere in this cell. It doesn't matter where. Most people put it at the end. You do a shift return and you get an answer. If you got a long keyboard, which most of you don't have, you can just do the enter key on the far right side and not do a shift. But most people have a smaller keyboard and you need to do shift return. And by the way, I can re-enter this and there's no problem doing that. I keep re-entering it. It gives me the same answer every time. but I am changing the input number and the output number as I re-enter it. It's not a big deal. That formula is a little weird looking. Like, why not multiply the e to the negative t through? To tell you the truth, I don't know why Mathematica defaults to this. So to multiply the e to the negative t through, I can do what's called a postscript function with a slash capital E expand. We'll do the multiplication. It's a little silly that it doesn't do it. Oh, you know what? K must have a value in here. I had done something before this class and K took on a value of 1. Let me clear the value of K and re-enter it. Okay, now you see it in me. So when you did separation of variables, that's what you should have gotten for the solution. 22 minus 17 e to the negative kt is what you should have gotten. How do you use this? It's our model. We need to solve for k by using the fact that it's 7 degrees after 1 minute. That'll help you solve for k. And once you've got k, you can figure out how long it's going to take to reach 20 degrees. And in both cases, you need logarithms when you're doing it by hand, right? You use logarithms. So I can, for example, do this. I can solve. Solve is an algebra solving command. Dsolve or dsolve value solves differential equations. Plain old solve with a capital S solves algebra equations. I'm going to set 22 minus 17 e to the negative kt. Yes, you do. Equal to 7 and solve for k. Yes, you need a capital E. Or you need to do a fancy looking E like this. You can do that fancy looking E by just copying and pasting it. Or you can do kind of something fun. Escape E escape. Oh no, escape double E escape to make the fancy E. But a capital E works too. Don't do a plain old lowercase e though. Because Mathematica will treat a plain old lowercase e as if it's just the letter E, not a number. Capital E represents the number E, or this fancy looking E. You want to write these notes down. You can watch the video after class too if you want to be reminded. It gives us the answer in kind of a weird form. Okay, involving the imaginary unit. The reason for that is Mathematica is trying to give the most general answer, and it involves imaginary numbers. If you put comma reals here at the end, that'll give you the real answer. And you can plug that into your calculator, or you can use / capital N at the end to approximate it. You should have gotten about 0.125163 for the value of K. I plug that into the function now. And solve for when this equals 20 to get the final answer. And by the way, if you put a decimal in like this, Mathematica, that's effectively like doing the / capital N right away. And I think it might give you the real answer right away as well. Yep, okay, though it says, it gives you a little warning, but you can ignore that. So you should have gotten about 17.1 minutes. 17 minutes and 6 seconds for how long it's going to take for the water to get to 20 degrees Celsius. Okay. You should be able to solve it by hand. Separation of variables integration. Using the logarithms, using your calculator to solve it, as I hope you were able to do. If you were not able to finish it, it's something to work on briefly after class, maybe, just to make sure you get the right answers here. Also on the homework, there's a difference equation approach. It's in the lecture, it's in the PowerPoint. You need that formula for finite geometric series. It's a little tricky, you got to be careful. Okay. Can Mathematica solve difference equations? Yes, it can, but I'm not going to take the time for that. I do want to take the time to also make a slope field here, though. So you're going to start learning about slope fields if you haven't yet, depending on where you are with the lectures and the reading. What's a slope field? Slope field essentially takes the right-hand side of the differential equation. In the textbook, the notation for that is f of y, and uses that right-hand side function for the differential equation to make a bunch of little line segments in a plane, a ty plane, where we're going to graph a solution, whose slopes match the outputs of that function based on the value of y in this case. Sometimes the right-hand side also depends on t. And so you also need the values of t. Let's go ahead and do that here with Mathematica. Based on the k being 0.125163, negative k times y minus 22, that is the right-hand side of the differential equation. That's the f of y. I'm defining that as a function in Mathematica. This is fine to do, and I think a good idea. When you define functions in Mathematica, notice there's an underscore after the variable. That is essential to do when you're first defining the function, but once the function is defined, then you don't need the underscore anymore. I'm defining this right-hand side function, f of y. That underscore is essential. Notice I'm putting a colon equals there. An equal sign would be good enough. I have a habit of doing colon equals for some other reasons when I'm defining functions that I'm not going to get into. Either way is technically okay. Either just a plain equal sign or a colon equals, not a double equal sign here, because I'm setting something equal to something else. It's not like I'm solving an equation. That's my right-hand side function. The basic code to make a slope field is vector plot with a capital V and a capital P. Square bracket, these are built-in Mathematica functions. Desolve value, solve, vector plot. These are things in Mathematica that do something. You could call them commands, you could call them functions. They take inputs and give you some kind of output. The output could be the solution of a differential equation or the solution of an algebra equation, or in this case, it's going to be a graph, a graphical output, vector plot. The first input is going to be essentially the right-hand side function, the f of y, but you have to do a little trick here. In curly braces, you put a 1 first, then comma f of y. The reason you need to put the 1 first is related to something we're going to learn about in chapter 2 called a vector field. This can make slope fields, but it also makes vector fields, which are kind of more general versions of slope fields. And we'll talk about that distinction in chapter 2 of the textbook along about 4 weeks from now or so. 3 weeks, three or 4 weeks from now. Just realize that when you're making a slope field, as is in the book in section 1.3, you need to put a 1 first, then a comma, then the right-hand side function. If this right-hand side function also depended on t, maybe in this kind of way or something, like representing external heating or cooling or something from a fan, then you'd have to put a t in there as well. That could happen, but it is a more complicated model. Then you put a comma, then inside curly braces again, you put the values of t that you're interested in plotting this over. Since we know the answer is like 17.1 minutes, oh, maybe -1 to 20 is a good plot range for the t values. It's like on a calculator, the x min and the x max, -1 and 20. Notice it's inside curly braces, and each of those things is separated by a comma. Each of these things in curly braces is one input into vector plot. This is representing the right-hand side function. Essentially, this is the t range, t min and t max. And then we need another comma for the y and another list for the y range. Oh, okay, our water is going from 5 degrees up to 22 degrees or so. Oh, I don't know, -5 to 25 might be a good window there. If I enter this as is, I will get a plot of the slope field, essentially, though it will not be quite as ideal as we might like. It's not going to look exactly like what you see in the textbook. But let's see what it looks like. Got arrows on it because it's drawing them as vectors. Can you get rid of those arrows? Can you make them just little line segments? Yes, you can, though I always forget how to do it. I always have to look up my examples. Vector style, maybe? You can always, when you start typing a command, you can look up information about it. Vector style. I'm forgetting. I should have reviewed it ahead of time. Vector, or maybe it's vector scale. Scaling. I'm clicking to look at examples here. Vector scaling automatic. I'm forgetting. In the Mathematica documents for the lectures, I think I do have the right thing to do. Okay. I'm forgetting things offhand. There's many things I remember in Mathematica, but there's many things, especially formatting commands, that I forget. And I got to look up my examples, or I got to look up in, when you see these information signs, you can look up examples in what's called the documentation center. And you learn Mathematica often just by copying and pasting examples and modifying them. Okay. So there is a way to get rid of those arrows. I'm not going to bother right now. You can draw the solution in here as well. Show will combine different graphic objects. Notice I put the vector plot inside show with square brackets. If I want to plot the solution here, this function right here effectively, I can copy that. I'm going to paste it into another command called plot, which plots functions. And there you see it. And you see that solution following the slope field. Why? Because that's how slope fields are constructed. I won't take the time to explain it right now. I do in the lectures. It is in the reading as well. Solution curves have to follow the slope field. Anytime you pass through one of these line segments, effectively, it's got to be like a mini tangent line to the solution curve. It's a very useful thing because quite often differential equations cannot actually be solved. You might say most differential equations can't actually be solved, but they still might be a model of something, and we can still use a graphical approach. It's called the qualitative approach. You can still estimate what solutions look like, even if you can't find formulas for them. That's a very useful thing, and it's quite common. It's especially the case with partial differential equations. And if you, for example, need to take fluid mechanics, as most of you might need to, at least if you're mechanical engineering, there's something called the, get this pronunciation right, Navier-Stokes equation for fluid flow. It's a partial differential equation. In the most general cases, nobody in the world can solve it. In fact, if you can even prove solutions exist in some sense, for the most general situations, you'll get $1 million. Seriously, there's $1 million prize for it. It's really hard though, because nobody's ever done it before. They've tried. Well, that's not even just finding, that's not finding formulas for solutions. I believe, if I recall correctly, it's just proving solutions exist in general cases. Now, there are special cases where I think it's more solvable, but in general cases with sort of arbitrary initial conditions and boundary values, I think it's unsolvable seemingly. But can you prove solutions exist? plenty of people try to approximate them. You'll try to approximate them with software in your fluid dynamics classes. But what if you're approximating something that doesn't exist? Well, people think they exist because they model reality and they use them to design airplanes and stuff. So they better exist. But mathematically, nobody can actually prove it. And if you can, you win a prize. It's called a Millennium Problem, and you win $1 million prize.